My research is centered on condensation phenomena and also on quantum computation and kind of the integration of both of those fields. And like David said, we'll be given a talk in a little bit later. So I'm excited for you all to hear that. And oh, and I'm in Indiana right now. That's where I'm calling in from.
Awesome. Thank you, LeeAnn. I see Aleks joined. Aleks, can you hear us? Aleks Kissinger?
Yes. Yeah.
Awesome. Welcome, Aleks. Just give us a 30-second introduction about yourself.
Hi. Yeah, I'm Aleks Kissinger. I'm an associate professor at the University of Oxford. I'm calling you from beautiful Oxford, where it's sort of late in the afternoon now. I'll be talking today a little bit about quantum software, particularly about compiling quantum software and quantum circuit optimization. Very happy to be here and excited to chat with some people that I might not have normally seen before. So yeah.
Awesome. Thank you, Aleks. Looking forward to it. So we're going to spend a few minutes going around and make introductions before we start your talk, if that's okay. So everybody can meet others. So Alexandra Raber is next. Alexandra, can you hear us? Going once, going twice. Okay, I'm gonna just follow the list. Alexei Galda, if you can introduce yourself.
Hi, my name is Alexei Galda. I'm a research assistant professor also at U Chicago, calling in from Chicago. I'm a condensed matter theorist by training, and lately I've been working on quantum computing, error mitigation techniques, specifically targeting superconducting systems like IBM. Really looking forward to these talks. Thank you.
Thank you, Alexei. I like your background. It's a nice tent overlooking an ocean.
Yeah, I wish it was true.
Balaji Ramamurthy.
Yeah, I'm a software engineer interested in quantum. I have my own meetup called Zen for Quantum, and I do host some meetups like that. Hi, yeah. So yeah, I'm doing a small study on Sanskrit as a quantum language and quantum computer language, and my own interests, some hobbies I have in quantum. Thank you.
That's great. Thank you so much. Konstantin Gankulea is next.
Hi, so I work for JP Morgan Chase. I'm leading a group called Advanced Computing. Part of it is quantum computing. So we have some public work. I won't be able to talk too much about anything else.
Great. Thank you, Konstantin. Debasish Banerjee.
Hi, my name is Debashish Banerjee. I am a particle physicist who's based in Berlin. So I'm trying to use quantum computing to solve some of the particle physics problems, but yeah, especially in high energy physics. Thank you.
Great, thank you, Debasish. Emily Hoffman.
Yeah, it's a good, I'm coming right after him because we're collaborators. I'm at the Perimeter Institute in Canada. And yeah, I have a background in condensed matter and lattice field theory. So we're working on simulating these models on circuits.
Awesome, thank you. Eric Bond. Eric, going once, twice. Okay, let's get to Ewout van den Berg.
Hello, everybody. I'm Ewout van den Berg. I'm a research staff member at IBM TJ Watson here in Yorktown Heights. I'm dialing in from New York. I'm currently looking at error mitigation techniques. So thank you.
Thank you, Ewout. Gavin Jones.
Hi, I'm Gavin Jones. I'm a research staff member at IBM as well. I work out of the Almaden Research Lab. I'm in San Jose right now. I actually manage the quantum applications group, and I work on quantum applications in chemistry.
Awesome, thank you, Gavin. Guan Wang.
Hello, my name is Guan. I'm currently doing research in Dr. Mazziati's group, and I'm currently working on using the current constraint in the 1RDM to study molecular currents.
Thank you. Harshita Gandhi.
Hi, good evening. I'm dialing in from India, and I'm an undergraduate student just exploring this field and hoping to get a career in this field.
Thank you. I got your notice about recording, so we will be doing a recording of the public talks. But thank you for joining us in person. It's from India. It's exciting.
Thank you. Thank you.
Julia Rice.
Hi, I'm a quantum chemist. I work at IBM Research Center in California, in San Jose. And I've been working on quantum computing with the larger quantum computing team, and in particular on quantum applications of chemistry.
Thank you. Great to have you. Jeffrey Cohn. Jeffrey Cohn, going once, going twice.
Sorry, yeah, I'm a little late. Are we introducing ourselves? Is that what's going on?
Correct. Just in 30 seconds, tell us about yourself and your interests and your area of research.
Okay, I work on the quantum applications team in Alberton under Gavin Jones, and my interests are mostly just in all aspects of quantum simulation, state preparation, time evolution, imaginary time evolution, and measuring other properties of quantum systems.
Great, thank you, Jeffrey. Matthew Roberts.
Hi, I'm Matt Roberts. I'm a post-bac. I was recently admitted to the University of Pennsylvania. I'm interested in exploring how category theory and quantum computing connect.
Awesome, that's my alma mater.
Excellent. I haven't got there yet. The COVID situation has delayed my plans a little bit, but I was admitted. I'm excited to go in, and I'm interested in eventually getting a PhD connecting category theory and quantum computing.
I hope you get to work with Benjamin Pierce. I was one of his first TAs, and he's a great authority in the category theory field. So that's exciting.
Thank you.
Yeah, I would be looking forward to see how you connect these issues. That will be fantastic. Miriam Beckens.
Hi, I'm Miriam. I'm a lecturer at the University of Birmingham in the UK. I work on the ZX calculus, so this is category theory and quantum computing. And I also work on applying methods from quantum computing in theoretical computer science more generally. Thanks.
Great, thank you. Thank you, Miriam. Nate Ernest Noble.
Yeah, hi, my name is Nathan Ernest Noble. I'm a quantum computing applications researcher at IBM, really focusing at how we can make use of pulse level applications on our software and access to the backends.
Great. Nick Braun.
Hi, Nick Braun. I'm also at IBM. I'm an experimental quantum computing physicist. I work with Nate.
Thank you. Welcome. Nicholas Savaya.
I am a researcher at Intel Labs. I focus mainly on quantum algorithms for Hamiltonian simulation and new applications in material science and chemistry. Thanks for putting this together, Alexei.
Thank you. Welcome, Nicholas. Great to have you. Finally, we meet in virtual space after the physical space. Nikhil Shah. Nikhil Shah?
Hi, I'm a DPhil student at Oxford University, working with a quantum group, mostly relating category theory with descriptive complexity.
Great, welcome. New York, Decare.
Hi, I'm a PhD student at Edinburgh. I'm also doing category theory and trying to find connection to quantum stuff.
Thank you, welcome. If you guys can just turn on video if it's easy for you during the introduction, would be great so folks can meet you. I think it really helps to kind of feel that we have almost like we're in the same room, if that works for you. Omar Shihab.
Hi, I have recently joined IBM as a quantum computing applications researcher. Previously, I've worked on quantum complexity theory, quantum programming language, and near-term quantum algorithm. Thank you for organizing this.
Absolutely, welcome. Quan Long Wan.
Hi, at Oxford University. I'm working on ZX calculus and quantum circuit optimization. Yeah, that's it.
Welcome. Rene Allerstorfer.
Hello, I'm a PhD student at QSoft in Amsterdam, and I currently work on protocols for quantum cryptography.
Welcome. Scott Smart.
Hi, I'm a graduate student at the University of Chicago with Professor David Mazziati. We're looking at applications of reduced density matrix theory for quantum computing, for molecular simulations, and just all different applications there.
Great, welcome. Sebastian Hassinger.
Good morning, Alexi. I'm Sebastian Hassinger. I'm with IBM. I run the academic partner program in the quantum team, and I sponsored this event, so I'm hoping it goes very well. And thank you for organizing.
That's amazing. It's been like only a few weeks when we met in an actual coffee shop when they existed to discuss this. And now we're all here from around the world. Thank you, thank you. Let's see. Scott Smart.
Hello? Oh, I think I just introduced myself. Did you hear?
Let's see. Yep. Sorry, I'm going down the list. My list is fluctuating. Simon Ewing.
Hi, my name is Simon Ewing. I'm a PhD student with David Mazziati. Lately, I've been working on introducing periodic boundary conditions to the variational 2RDM method that I'm sure you'll hear more about today.
Awesome, looking forward to it. Terrell Franz.
Hi, folks. Good to see some of you. I know I'm an associate professor at Harrisburg University in central Pennsylvania. My research is generally on organizational networks, and I study mergers and acquisitions. From that regard, I'm transitioning from classical to quantum to see how quantum will work in that space. But for most of my time recently, I've been focused in on workforce development, kind of like Nate, except more on the outside of IBM world.
Great, welcome. Let's see, Yael Ben-Haim.
Hi, I work in IBM research, and I'm a developer in Qiskit, which is our open software for quantum.
Great to have you. Alexander Bolton McKeon.
Yeah, hi. I'm a grad student in applied physics at Stanford, and I'm very interested in both the experimental and theoretical sides. So looking forward to hearing more about this talk.
Welcome. Andrew Edens.
Hi, my name's Andrew. I'm with IBM out in California, and I'm working on quantum simulations and demonstrations. Thanks.
Welcome. Let's see. Anthony Schlimgen.
Hey, good morning, everyone. I'm a postdoc at Los Alamos National Lab, working quantum chemistry of the heavy elements.
Welcome. David Ferrari.
Hi, I'm a PhD student from Parma, Italy. I work on quantum compilation and quantum networking.
Welcome. So I'm glad we set it up in the morning so your folks in Europe can join. That's great. Benita Zazueta.
Hello, everyone. My name is Benita. I work with Sebastian Hassinger on the IBM Quantum Academic Partnership team.
Great to have you here, Benita. Welcome. Let's see. My list is actually fluctuating. That's very interesting. It's not a trivial task. We need some quantum computation to do it properly. If I missed anybody, please just introduce yourself. Let's see. If first of all, raise your hand. Let's do this. If you haven't introduced yourselves yet, there is a feature in Zoom where you can raise hand. I will see that. I can call for, and I probably can just call people who have the hand raised. Okay. So raise your hand if you have not been introduced yet. Okay, great. Jin Sung Kim.
Hi, my name is Jin Sung Kim. I'm a researcher with IBM. I work in the demonstrations team.
Welcome, Jin Sung. And now you can lower your hand so I see that. Okay, great. Alexander Raber.
Hi, I'm Alexandra River. I'm a graduate student in David Mazziotti's research group at the University of Chicago. I'm working on studying molecular conductivity using the 1 and 2 RDM reduced density matrix methods.
Great, welcome. Now we can lower your hand and then I will see the, okay, Jonathan Candelaria.
Yes, my name is Jonathan Candelaria. I'm executive director of a System X program at Stanford, but I'm also the interim chair of the Workforce Development Committee in the QEDC consortia.
This is great. It's great to have locals because initially we planned this will be Quantum Conversations West, and we'll join the West Coast institutions, but we expanded to global meeting, of course. Hopefully, once the restrictions are lifted, we'll be able to host local meetings. So it's great to have folks from Stanford. Welcome. Let's see. Is there anybody else who haven't introduced themselves yet? If so, raise your hand. Or you can just do it now in the open floor. Okay. So I think everybody introduced themselves. It's great. It's great to have all of you guys. It's really amazing how we can have the global community together in these times. So I think it's a silver lining. And I think we now can proceed with our first talk. We have Aleks Kissinger from University of Oxford. I put the description on the site. So Aleks, I've made you the host. So now you should be able to present, and I'll let you introduce yourself and your research group in more detail. Welcome, Aleks.
Okay, hi everybody. Thanks again, Alexei, for setting this up. This is, I think we're all trying to get used to this new format, and it's nice to see that along with a bit of the weirdness, there are kind of some new opportunities for doing stuff that wouldn't have been so possible before. Right, so I already introduced myself. I'll say it again for people that came late. I'm Aleks Kissinger, associate professor at Oxford in the computer science department, in the quantum computing group, which is sort of an unusual quantum computing group in that about half of us or more are category theoreticians. So you might have noticed a couple of them sort of speckled amongst the group here. I mean, I won't talk too much about category theory today, actually not at all. But some of these ideas sort of grew out of that. And that explains at least kind of half of my talk title. Let me see if I can share my screen. I'll share, okay. And I guess that sort of explains the structure part of the title of my talk. So it's quantum circuits from structure to software. And well, maybe I should just, rather than waffling about what that actually means, just kind of dig in. So this is a talk about quantum software. And if you see people saying quantum software, you often they mean one of two quite different things. On the one hand, someone could mean the code that runs on a quantum computer, right? So quantum algorithms. And there's the famous algorithms for factoring and search, and these days lots of other stuff. I have a question, which is maybe a bit of a generational divide, or maybe a Western Hemisphere versus Eastern Hemisphere divide. Does anybody know who's pictured in that factoring picture there?
Pauly Shore.
That's Pauly Shore. So the keen eye would catch that this is not in fact Peter Shore, but Pauly Shore, famous for his roles in numerous stoner comedies in the 90s. Anyway, that's kind of one meaning of quantum software is algorithms. Another meaning is not really the code that runs on a quantum software on a quantum computer, but the code that makes that code, or rather the code that makes that code better. So by this, you can mean compilers, so things that turn say, high-level software into something that's actually runnable on a machine. Something me and my students think a lot about is optimization, so making computations run faster. Verification, here I mean verifying that the code you got is actually doing what you think it's doing. And things kind of in that general genre. So this is really thinking about kind of the structure of software and how can we make it kind of as fast and efficient and correct as possible. Okay, so until recent years, if you worked in either of these areas, a common criticism would be that this is pointless. There's no quantum computers. By now, we all know that that's not true anymore. There are quantum computers, but they're a bit rubbish. Right? So, you know, we have this catchphrase now, NISC, which is somehow a handle for these not very good quantum computers that we have. These noisy intermediate scale quantum computers have short coherence times, small amounts of memory, typically operations, say gate level operations, measurements are very noisy, and we have limited connectivity. So if, for instance, I want to do something involving 2 qubits, I can't do it between an arbitrary pair of qubits. I really have to do it between things that are neighbors. And this is definitely true for superconducting devices and for most of the kind of ion trap type proposals. But I think this is actually a nice place to be if you're working in quantum software, because you can come up with a small kind of stupid idea, and if it makes the software just a little bit better, this is actually increasing quite a lot what you can do with these very limited devices. So I've been talking kind of about code and about software, but really what I'm thinking about when I'm saying these words is quantum circuits. So quantum circuits are kind of like an assembly language for quantum computation. They consist of sequences of primitive operations, which are kind of run in order on some register of quantum memory. Right? So you can really think of this as sort of an assembly code like this. But we also get used to thinking of it more as this kind of 2D notation, where you see your memory here and time kind of flows this way as different operations get applied. Right, so now let's think about this little circuit and think about how we could make it run faster or better, right? So running this circuit with fewer gates is just going to be better, because these gates introduce noise and they take time. Okay, so a very simple thing we could do to make this circuit smaller is, if we know a little bit about how these gates kind of interact with each other, we can start to transform this circuit into something that's equivalent but runs faster. Okay, so a very simple thing that we might try is these things. So these C0 gates interact with Hadamard gates in a certain way, which is that I can take a pair of Hadamard gates and sort of push them through a C0 gate, and it kind of flips it around. Okay, so let's see that. I push those Hadamard gates to the right, and the C0 flips around. Okay, so when that happens, now I have a pair of C0 gates, and these things cancel out with each other. Okay, so now by doing some little simple moves on gates, I have a simpler, faster circuit. Right. So you can start to come up with a lot of these identities. Right? So here's a pair of C0 gates equals a C0 and a swap, and here's the thing I showed, and here's some Z gates and other things about C0s and so on. And then maybe you would come up with some more of these identities if you thought a bit longer, and then you would come up with some more, and then some more, and then some more. And at some point you start to wonder, when does it end? Like when do I know that I've got all of the right identities to really do a good job at optimizing my circuits? And I mean, the answer is you don't. It's purely a heuristic thing. You just keep kind of throwing in the kitchen sink and seeing how well it works, or at least that's kind of how this kind of optimization is done these days. However, you can also do something that's a bit more clever, which is I can look at this circuit and think of these gates not as primitive things, but actually as built out of even more primitive stuff. Okay, and now there's a few definitions for what might be more primitive stuff. The kinds of things me and my collaborators like to work with are these things, which are called spiders. So these red and green dots, which are labeled by angles like this, are called spiders. This green one is called a Z spider. This red one is called an X spider. And put together, these make what's called a ZX diagram. Okay, so I'll explain a little bit about what these things are. So there's a few perspectives you can take on these things. And actually, if you go way back to, well, I say way back, if you go about 10 years back, the perspective might have been something about category theory, right? But let's not talk about that right now. Perspective one is ZX diagrams are really just like circuits, but instead of being made of unitary gates, they're made of these special gate-like things called spiders. Okay, and there's two kinds of them, as I said. There's the Z spider, which if I draw the matrix of this thing, it looks like it's got a 1 right up here in the top. It's got an e to the I alpha right down here in the bottom, and it has zeros everywhere else. Okay, so if it's got one leg in and one leg out, okay, so I suppose I should say this is a 2 to the, if this has m inputs and this has n outputs, then this is a 2 to the m by 2 to the n matrix. Okay, and if this thing has one input and one output, then it's a 2 to the 1 by 2 to the 1 matrix, and it's actually this matrix, which if you are used to playing around with circuits is just a Z phase gate, which sometimes you see written as RZ alpha. Okay, so you can see this is a kind of a massive generalization of these kinds of phase gates. Okay, so that's the Z spider. The X spider is almost the same. It's just rather than doing everything with respect to the standard basis, we do everything with respect to this Hadamard basis, the plus and minus basis. Okay, so really this thing is just the same as that thing up to a change of basis. Okay, so that's one perspective. I heard a couple of people mention they're in condensed matter, so maybe perspective 2 is something that they can appreciate, and maybe some others as well. ZX diagrams can also just be thought of as tensor networks. But whereas usually the way we think about tensor networks is as some black boxes kind of wired together and we don't really say what's in the boxes. These things, we use two special kinds of boxes which are parameterized by a single angle. So we have the Z boxes, which are kind of like a Kronecker delta times this phase. And the X boxes, which are this other kind of thing. Okay, so you know, you could say, well, I'm not sure, these don't look that natural, so why would we want to fix these as our choice of boxes? Oh, well, maybe I should say one thing before I get to that. So the difference really in a ZX diagram and a circuit, or I'd say the biggest difference, is ZX diagrams, like tensor networks or friends, are bendy, in the sense that they're very flexible. So you tend to think of a circuit as this kind of rigid thing where I have gates kind of happening in sequence and in parallel. Whereas ZX diagrams, if I take this picture here and I deform it to something where the graph is the same, this is actually still the same linear operator. So it inherits this nice property of tensor networks that the only relevant thing here is the graph. So it's what is connected to what. Okay, so this thing is equal to this thing is equal to that thing because they're all just deformations of each other. Okay, so now here's the thing I was getting ahead of myself to say. A reason to look at these generators, well, one reason to look at them is they are universal. in the sense that they actually generate all linear maps, or at least all linear maps on powers of 2-dimensional space. And they're handy for building most of the common gates that you would see in a quantum circuit. Okay, so these, I already showed you how Z phase gates are written as just these one input, one output spiders. Some familiar special cases are the S gates and the T gates. The Hadamard, which we often draw as just a little yellow box like this, can be written as a green, red, green, sometimes called the Euler decomposition, if you're familiar with these things. C naughts just look like a kind of more colorful C naught, and CZs look like a pair of green dots connected by a wire. Okay, so these are very common gates in the toolkit of somebody building circuits. They're easy to express with spiders. So that's nice, but what's nicer is that these spiders satisfy some algebraic identities, which together are called the ZX calculus. So here we have 1, 2, 3, 4, 5, 6, 7, 8 laws that these spiders satisfy. And these 8 rules actually imply all of those pages and pages and pages of gate equations that I showed you before. Okay, so they have a very nice compact structure that lets you work very effectively with these kinds of interactions between gates. Okay, so let's see this in action. So here's our little sample circuit. We're going to take these gates and slice them open, and we see that there's actually spiders inside. And now we'll apply some of those rules. And now I have to anticipate what I'm going to do. I believe the first thing I'm going to do, or the first rule, is that spiders are the same color. So these green ones and these red ones confuse together to make bigger spiders. So that's what's happened there. Right? So you can see that these actually 4 spiders here have all squashed together, and they fuse together, and their angles have added. Right? So here's a pi by 2, a pi by 2. The blank ones count as 0. So if I add all their angles together, I get a pi here. And a few more things have fused. And then the next thing that happens is if I have a red spider and it hits a green spider, it actually copies through. Okay, so if I look at this dot hitting this other dot, it copies through and it makes 2 copies of itself. Okay, and then we can fuse these red dots some more, yeah. We fuse some dots some more, and then we can fuse some dots some more. Another thing that happens is if I have a pair of parallel edges, these things disappear. Oh, I haven't done that yet. Yeah, there we go. A pair of parallel edges disappears. We can fuse some more. And at some point, we get a much simpler diagram. Okay, and this thing, if it has a nice enough structure, I can pull a circuit back out. This obviously has a very simple structure, which is just some product state of my outputs, right? So I can prepare that state using a quantum circuit this way, for example. Okay, so now a question becomes, how can we do this by hand calculation, which was involving about 30 spiders, on thousands of spiders? Okay, and you might say, well, actually, you know, current hardware is pretty small scale still. You know, we're talking about 10 to 50 qubits. But as soon as you start talking about, say, 50 qubits and a gate depth of 20 or something like that, you're already getting into the regime of thousands of spiders. So it's not practical to do this kind of thing by hand. So how do we scale up? And the obvious answer is we need a tool for doing this, some software for working with these things. Okay, so we have a tool. It's called PyZX, right? So some people say PyZX, but according to us, the developers, it's pronounced PyZX, which is like if you say physics, but then you don't pronounce the H, it's PyZX, okay? And this thing is a Python library, which you can use from Jupyter notebooks, and you can sort of interconvert things to Qiskit and well, do quite a few different sorts of stuff, which I'll show toward the end. and give you some more details on how you get this tool. Okay, so maybe I should let the slide do the talking for me. So PyZX is an open source tool for quantum circuit optimization, verification, and classical simulation using the ZX calculus. Okay, and the main idea it uses for automation is actually quite a simple one. So if you're a human and you're clever, you can work with these things, right? Equals means that I can use my human cleverness to decide whether I should replace this picture with this picture, or if I should replace this picture with this picture, right? And, you know, maybe a machine can have some kind of strategy of knowing which way to go, but you know, it needs to use some smarts. But one thing that the machine is already capable of doing is if I just tell it which way this rule should go. Okay, so clearly this thing with one dot in it is simpler than this thing with two dots in it. So I'm just going to direct this thing. Okay, and that's effectively the difference in what's called equational reasoning versus rewrite theory. Okay, so the idea is to turn some equations into rewrite rules, or derive some rewrite rules from equations, and now just tell a program, which is called a simplifier, to just apply these rules until it can't apply them anymore. And then when that's done, so at some point, as long as my rules are always making this picture smaller, this thing will terminate. And when that's done, try to extract some meaningful data from the simplified thing. So often that's either a smaller circuit or some simulation data like amplitudes or probabilities. Okay, so the first thing we tried this technique out on was something called T-count reduction, which is exactly what it sounds like. It's reducing the number of T-gates in a circuit. So in this ZX diagram notation, a T-gate is just a green dot, which is labeled by an angle which is a multiple of pi by 4. So I guess technically this thing is a T dagger gate, but anyway, we call these all T-gates. So why do we want to reduce the number of T-gates? Well, one reason comes from fault-tolerant quantum computing. So we have these sort of long way off schemes for doing quantum computing fault-tolerantly. And what they tell us, or at least almost all the schemes that people have studied, what they tell us is that if we want to do Clifford gates, which are basically everything in this picture which is not a T-gate, these things are easy. And if we want to do T-gates, they're something like 100 times as hard as the Clifford gates. Okay, so if, for instance, we can get rid of 6 T-gates here, that's as good as getting rid of 100 of the other gates. Right, so this motivates why you would want to get rid of them. Okay, and the way we do this with PyZX is we take some circuit like this, and we compute its reduced ZX diagram, which in the process has eliminated some T-gates. Okay, so some of these T-gates sort of find each other and fuse together or cancel out. And then from the simpler diagram, we extract a circuit back out again. Okay, and if you're not so good at counting on the fly, I think there's about 6 fewer T-gates down here. So like I said, that's saved about the effort of 600 of these, say, C0 gates or something. Okay, so we tried this on a bunch of benchmarks. And in the particular case of what's called ancilla-free T-count reduction, so this is without using extra memory, we did pretty well in that we matched on something like 72% of the circuits we looked at, we matched the state of the art. And on about 17%, we actually did better with this kind of technique. So when we first got into this, actually, Earl Campbell, who's the Campbell here, emailed me to say, welcome to the T-Wars, because there's actually quite a few people working on this. And pretty much immediately after we produced these results, another group came out using a different technique and matched all of our numbers. But then later in 2019, so this was in spring of 2019, in winter of 2019, a couple of Oxford folks, so Harney Wong, who introduced himself about 30 minutes ago, I guess 20 minutes ago, produced another technique based on ZX calculus, which then got ahead of the state of the art again. So this is really kind of, I think the T-wars is the right word for what's going on with this at the moment. Okay, so that's kind of what I wanted to say about T-count. So something that was kind of pleasant about this kind of technique, and actually you can use this for a lot of techniques based on simplifying circuits, is that they are self-checking. So what does that mean? That means if I have a circuit like this and I optimize it to a smaller circuit, well, then the smaller circuit had better be doing the same thing as my bigger circuit. Otherwise, I've introduced some errors into my code. So one way I can check that is if I have two unitaries which are equal to each other, then doing one and then undoing the other should be equal to doing nothing, right? Which in this kind of language is the identity gate, which I've just written as 1 here. And it turns out this simplifier, if it simplifies C to D, it'll also simplify C and undo D to nothing. So we were able to run this kind of checking procedure on all of our optimizations. And it did say yes, thumbs up. But I should mention this, well, I should say one more thing, which is so yes, it thumbed up kind of all of our outputs. Actually, along the way, we found quite a few bugs when this thing was giving us a thumbs down, and we fixed them. But interestingly, we ran this on some other circuits from the literature, and it actually found some bugs. So this one here was a circuit that was actually published in a peer-reviewed journal, and it was just wrong. So our verifier found it, and we were able to well, what it said is this thing might be wrong, and then we were able to use a different technique to prove that it actually was wrong. Okay, so one little caveat here. This doesn't prove that our code is correct, because our optimizer and the thing that checks it could both be wrong. But it's lightweight in that we didn't really have to do any more work to do it. So it didn't cost us anything. And it actually builds confidence that our techniques are working correctly, because it's actually quite unlikely that these two quite different procedures are sort of conspiring to convince us that they're both correct if they were both wrong. So I think these kinds of techniques are actually really useful, especially here in these early days of developing quantum software. Especially because it all happens before we fire up the quantum computer, right? So if you know the kind of frustration of getting something to work right when you're sitting there waiting in a queue to run it on a quantum computer, you can appreciate doing as much kind of offline as possible. Okay, so that's what I wanted to say about verification. The last thing I was going to mention a little bit about is circuit routing. So I mentioned a little while ago that these NISC architectures have limited connectivity, which is something I guess a lot of people here will be familiar with. So if I want to do a 2-qubit gate, say on this is I think this is a Rigetti architecture. If I want to do a 2-qubit gate between qubit 14 and 13, that's fine. But if I want to do a gate between 13 and 6, that's not fine. So naively, what I would do is I would start to swap this thing around, and I would kind of bring it over here, do my gate, and then maybe even, if I'm super naive, bring it all the way back here, right? So I'm doing 1, 2, 3, 4, 5, 6, and then my gate, 7, 8, 9, 10, 11, 12, 13 gates to do a single gate, right? So this is obviously never going to be the right way to do this. Okay, so there are a lot of techniques for actually turning your logical circuit into a routed circuit. One that we've been thinking about exploits thinking about this circuit extraction procedure. So I didn't really tell you much about how we extract circuits from ZX diagrams. For people that are interested, I'm happy to explain some more. But the kind of basic idea is that it's a sort of Gaussian elimination type procedure. And the way we do it is not unique. So actually, if you choose which row operations, let's say in the Gaussian elimination you do, if you choose which CNOT gates you do respecting some constraints, you can actually extract the circuit in a way that only produces CNOT gates or 2-qubit gates between neighbors. Okay, so if you think about this as a kind of 9-qubit architecture here in this sort of 3x3 grid, and each of these is a time step, then you can see that the CNOT gates are getting applied only between neighbors at each time step. Okay, and this is the kind of extractions we can do. And actually for CNOT circuits, this works very well. So comparing this kind of technique to more general purpose techniques. So here's Rigetti's Quill compiler. And at the time, it was doing a lot better than Qiskit even at these things, but you know, this is changing fast, so I don't want to make any 2020 claims about this. But comparing to Rigetti at the time, we were doing up to 5 times better at routing CNOT circuits using this kind of technique. Okay, so that's about it for the kind of talking part of my talk. I also wanted to give a quick demo of the tool and just show you some of these things in action. Maybe before I do that, I could ask if anybody has any questions or comments or things that they want to pop in and say. I'll give you a minute to do so because sometimes it's hard to find the mute button.
Yes, let's play it by ear. So just unmute yourself, folks, and ask a question. If we see too many people asking, we'll try to sequence it. But for now, I think we'll just open the floor. You can always type at the speaker in the chat also to ask your questions.
Mm-hmm. Let's start with anarchy and then scale back from there if necessary.
Exactly.
So I have a question about the T gates. On the IBM hardware, a basic gate is Rx5/2, right? Which is not RZ. U1 is actually considered kind of free, so they are swapped, right? So the T gate on IBM would be Rx5/2.
Oh, okay. Yeah. Because the Z rotations are purely a classical update. Is that right?
That's my understanding.
Okay. Yeah. And so a nice thing about this choice of generators is everything is color symmetric. So actually, if you flip all the reds and greens everywhere, which is the same as flipping the role of Z and X everywhere, everything still works exactly the same way.
Yeah, thank you.
Okay, maybe I'll just start the demo, but feel free to jump in, anybody who wants to say something or ask something. Okay, so here I am in a Jupyter notebook. Normally, if you want PyZX, you can just pip install PyZX and not worry about this stuff. So I'll just import PyZX as ZX. Now, a very simple thing I can do, I guess some of you will recognize this CHASM format. This is just a very simple text format for writing circuits. So here's a register of 4 qubits, doing CNOTs between some combinations of them and then a T gate, which if I draw that, looks like this. Okay. And another thing I can do is I can actually turn that thing into a graph or a ZX diagram. I can draw that as well, and it looks identical. But one thing you should bear in mind is that this thing is kind of more than a circuit. it really is a graph. So if I just pick these things, I can sort of move them around, and I can see that this is actually just some graph, which encodes this circuit. Okay, and here's a simpler thing. And if I look at these circuits before turning them into a graph, then this is just a list of gates, which is probably pretty familiar if you're used to working with something like Qiskit, this kind of circuit format. If I turn it into a graph, it really is a graph. So this thing is a graph with 14 vertices and 15 edges. Okay, but the way we draw it, of course, it looks identical. Now, a very simple way I can simplify this graph is to use what's called the spider sim. So simplify, let's see if I can get it to complete here. Yeah, has a bunch of simplification procedures, but I'll just call the spider sim, I think, on G. And what this will do is just fuse together dots of the same color. All right, so this didn't do very much in this example. I believe it fused this one and that one together to make that, fused this one and that one together to make that, but it couldn't do anything else. So it did the rule once and then once again. So that was in 2 iterations. Now, if I call full reduce, which is our sort of kitchen sink simplifier, then what you see is that this thing reduces all the way to a swap. Okay, and if you look at this circuit, you can see that I kind of contrived it that way because these things are C0 gates, which a kind of exercise you learn in Quantum Info 101 is if I do 3 C0 gates in this setup, this makes a swap. And then I can see that this red pi/2, which is like an X pi/2 rotation, goes and cancels with this 3 pi/2, and this pi/4 cancels with this 7 pi/4, and leaves me with the swap gate. I wonder, so I'm going off piste here, this might not work, but if I turn that off, no, it didn't work. So never mind. I was thinking that that might get me this kind of output, but anyway, this sort of thing always happens when you're giving a live demo. So it supports input in a number of formats. Something that is a bit hackish is this thing called squasm, which is just spider chasm, which is if I just make a register with a capital letter, that will plug in a dot of the same color to the left and plug in a dot of the same color to the right and already do all the fusions that it can. Okay, so I use this kind of squasm thing. I think I can actually turn off simplifying first so you can see what happens. Then this bit is just a circuit, right? And that made this middle part. And then it plugged in a green into the front and a red into the back. And then if it does do the simplification, which is the default behavior, I get this thing, which is not a circuit anymore. Or at least it doesn't look like a circuit anymore. Right, so I can also make more complicated looking things. I think this should be just zx.draw. Okay, so here I've got a pair of these things hooked on. Now these are a sort of thing that we study quite a bit called a phase gadget, which what this actually does is it applies this phase whenever the parity of these inputs is equal to 1. So if it applies that phase whenever the parity is equal to 1, and then it undoes that phase whenever the parity is equal to 1, then the total effect of these two things is to do nothing. Okay, and I think if I apply the Clifford simplifier, it can't figure that out, which is a kind of simpler simplifier. But if I apply the kitchen sink one, it does, and it reduces that to the identity. Okay, so as I said, this thing loads in quite a few different formats to varying levels of success. So supports CHASM, this .qc format, the QSIM format, which Google published its supremacy circuits in. So here's what one of them looks like. Okay, and this is their fsim gate, which is a sort of a swap and I think a Pauli ZZ with a given phase, something like that. Okay, so here's what it looks like drawn flat. Okay, which is just some big circuit. I can also draw it in a kind of a three-dimensional way. And what you'll see is this circuit is actually involving a register of qubits, which is two-dimensional. It's 3 qubits wide and 4 qubits tall. So this is one of the smaller ones. It's not the full-size ones. And what you'll see is that the fsims are actually only happening between nearest neighbors. Okay, so here's a qubit, and here's the one directly below it, and an fsim's happening, and then so on. So this is happening to the middle layer, and then this is happening to some other configuration of them. This is happening to some other configuration, and so on. And if you go read this paper, you can see that they explain how these different iterations are done. And if I apply full reduce to that, I get something that is somewhat reduced, but not that reduced, because, well, if I'd come up with a way of reducing these things very small, then I could classically simulate them, and then I wouldn't be telling you all about it before I wrote the paper and got all the credit. So that's a bit about kind of the basic features. Here's a little t-optimizer that I've just wrote by chaining some of the built-in functions together. Okay, here's a smallish circuit. I think this is a 5-qubit Grover. Maybe it has some ancillas as well. Looks like so. It has 336 T-gates in it. If I apply this T-optimizer, another circuit comes out with 166 T-gates. Okay, and now I could check that this thing is in fact equal to this thing by calling this circuit dot verify equality, and I give it another circuit. And it says true, but you know, I could have just waited for a few seconds and printed out true. So I'll show you what's kind of going on under the hood. Here I've made a copy of my simplified circuit, and I've hooked the adjoint of my original circuit onto the simplified one, and then I've simplified it, and that's what this full reduce did. And I see what came out is actually the identity, which is, in circuit language, it's just a bunch of wires with nothing on it. Okay, and if I take this thing and if I mess it up a bit, so let me show you C1.gates at 10 is actually a C0 gate. Okay, if I change that to something different, here's a T dagger, and I verify equality, it says false. And if I kind of do the same thing as I did before and see what's going on, then my reduction actually didn't terminate with the identity. It did terminate, but it gave me something which was not an identity circuit. Okay, so that doesn't tell me that they necessarily are not equal to each other, because in fact this is a hard problem. This is a QMA hard problem actually to determine equality. But what it does tell me is it wasn't able to prove that they were equal to each other, which is a sign that something might be wrong. Okay, and here something obviously is wrong in that I've messed up this circuit. Okay, so another way you can use PyZX, so this is running on my machine. Hopefully this hasn't died in the meantime. Is on the quantum experience. So PyZX is available over pip, and I discovered quite interestingly that I can just pip install things inside of a QX notebook. Okay, so we got PyZX here. I don't know if this whole demo is going to run, but it's not it's not too much of a problem if it doesn't. So here we already have PyZX. Just load this. I'll load PyZX. And here's a very simple little wrapper for turning a ZX diagram into a Qiskit circuit. Okay, so that's a bit of glue that I kind of hacked together in a few minutes. And now here's Burlington. Let's see if this will come back to me in a reasonable time. Here I'm going to build a little ZX diagram. Okay, so what did I do? I created some vertices here. I hooked them together with some edges and I drew it. So here's this thing. This thing is not a circuit, but I can turn it into a circuit by doing the circuit extraction. So here's what it looks like, Qiskit circuit. And now here's the part that, you know, let's see if this will come back in time that, ooh, job is actively running. And that's, I guess nobody watching right now is sending jobs to Burlington, which is good. Job is successfully run. And I get the results. And the ZX diagram, so this thing, if I plug in 0, 0, 0, I should get 0, 0, 0 out of it. And Burlington agrees. Well, 75.4% of the time. Okay, so that's about it. That's what I wanted to say. So thanks everyone. I'm happy to answer questions.
Yeah, I have a question. This was great. I was wondering, is there any companies using this to your knowledge?
Not to my knowledge. I think so. Cambridge Quantum Computing plays with PyZX, I think, but I don't think they're. I mean, I know that their compiler doesn't actually use PyZX under the hood, but we talk to those people quite a bit. Yeah, I don't know. I think maybe some of these ideas from it are starting to kind of get out there into the wild, which I think is nice.
Maybe I can comment, Alex.
Yeah.
So this is Ross Duncan from Cambridge Quantum Computing.
Hello.
So the ticket compiler doesn't actually use PyZX itself, but it has some of our own implementation of some of the parts which are in PyZX. So we use some ZX calculus things in a slightly different way.
Cool. I'm glad you're here. So you didn't force me into a situation of saying something that was maybe wrong about what you guys are actually doing. So. Other questions?
Yeah, hi, Alex. I have a question. Can you hear me?
I can hear you very softly.
Yes, please speak up. Turn on.
Okay. Is there any way to put in, like, say, additional constraints, such as, like, you know, right now 2-qubit gate errors are like the highest source of errors, opposed to single qubit gate errors. So to kind of like add additional structure to this kind of simplification.
So one thing we're thinking about a lot is this extraction phase. It's not unique, and it's quite sensitive to doing it in a clever way. And if you do it in the wrong way, it actually ends up generating a lot of 2-qubit gates. So we're thinking about how to get that number kind of as low as possible. So in that sense, it's kind of always the goal to produce as few 2-qubit gates as
right,
possible.
for like current state of the art superconducting qubits, like two qubit gates are kind of the main error. You know, I would say T gates are for error corrected, or for an error corrected quantum computer. So each kind of system has its own kind of thing you want to get rid of.
Yeah, that's right.
And I think ions would be different from superconductors because you can use the motional degree of freedom. entangle. So I was just, I guess, interested in a little bit more hardware structured simplifications.
Ah, right. Yeah. Yeah. I mean, so we kind of started with the T stuff because that's what the people around us were talking about at the time. But these days we're thinking a lot about 2-qubit gates as kind of the main next target for this kind of thing. Something I didn't mention, actually, a useful application now for getting rid of T-gates is classical simulation of circuits. So there's these stabilizer rank techniques which go exponential in the number of T-gates in your circuit rather than the number of qubits in your circuit. So there it's actually useful to do a little bit of simplification beforehand, get rid of the T-gates.
Cool, thanks.
Other questions? If not, let's all thank Aleks. It was a great presentation. Thank you, thank you. Feel free to unmute and clap for Aleks, or just show, clapping hands on the Zoom. That was great. And, great screen sharing. It's really great to see Jupyter and everything. It works smoothly on my end. I hope everybody was able to see it well as well. So that's awesome. I see we have some more folks joined us after the initial introduction. So in case you just joined us or joined during the talk, thank you for joining. We did quick introductions when we started, about 30 seconds per person, just to say your name, your affiliation, and your area of research and your interests. If anybody is here who didn't do that and would like to introduce themselves, please raise a little hand using the Zoom raise hand feature. I can see you and I can call your name to give a brief introduction. I'll give you a few moments to find that. Or just feel free to go. Okay, William Swope, please.
Hi, my name is Bill Swope. I'm in California. I work for IBM in the research division. I report to Gavin, who was introduced earlier. And my background is quantum chemistry, basically a general computational chemistry and mostly statistical mechanics. But lately I've been working in the quantum chemistry area.
Thank you, William. And now you can lower your hand, please. Ross Duncan.
So yes, so I'm Ross Duncan. I work at Cambridge Quantum Computing in Cambridge in the UK. My background is from categorical quantum theory and the ZX calculus in particular. And nowadays, I'm mostly interested in compilation of quantum software. Thank you.
Great. Welcome, Ross. I think, let's see, Kevin Krasulich, have you been able to introduce yourself yet? Let's see. We can't hear anything. Okay, great. So we still will have time, after the second talk to add more introduction. And so the plan is, just to recap, during the talk, which is on the agenda, or any other talk, feel free to chat. Basically, the chat is structured so that the host will see your questions, and the host is the current speaker. So that way, the speaker can decide if they want to answer the question during the talk, or they want to defer it to the end. And obviously, after the talk is done, there will be Q&As. So it's really up to the speaker how they want to manage it. So feel free to use the chat feature for this. If there is any problem on your end, please email me. My email is alexi@chiefscientist.org. It is at the event webpage, quantum.sv. So I put it there for the whole world to see and use. So if you, for instance, decided that you want to give a talk at the next meeting, which will hopefully will hold monthly as a structured agenda part. Just email me there with your ideas or any other suggestions, right? So we're basically creating this format as we go. So it's very exciting. I'm open to all kinds of suggestions and certainly appreciate your feedback. All right, so let's see. I think if there are any questions, suggestions about the running the meeting itself.
Alexi?
Yes.
Somebody just made a good point, which is I didn't mention the GitHub link for the tool, so I'm just going to put that in the chat.
Oh yes, please do. Please do so, and everybody can see that. Yes, and also what I'm going to do, if you guys want to share, I'll copy this link and I'll put it on the event page as kind of follow up, right? So that way folks can always go back. So if you miss something, go back to the web page quantum.sv and see if it's there. If it's not there, email me. I will be able to recover any links and share it with you. Great. So our next talk is from University of Chicago, and David Mazziotti will start. So David, I'm going to make you host right now.
Okay, great.
See. 1 second. I'll do that. All right. So now you're the host, and now you should be able to share a screen. And welcome, David.
All right, excellent. Thank you, Alexi. Let me come down here, get the screen sharing started.
And please feel free to introduce yourself again, because I think some folks joined us during the initial part, so I think we have some newcomers.
Okay, sure. Let me just get this started here. All right. Okay, great. All right, so I'm David Mazziotti from the University of Chicago. LeeAnn and I will be presenting some of our recent research today. I want to thank Alexi and Sebastian for the invitation to the meeting. I think this is great, Quantum Conversations by the Bay. It's really great, especially in these times, for all of us to get together and enjoy science. So definitely, if people have questions, during the talk, that's great too. You can use the chat, or you can also just save your question up for the end as well. So all right, let's get started here. I hope everybody's having a good day and staying safe. So the talk today is preparation of an exciton condensation on a 53-qubit quantum computer. So the outline of the talk, we're going to start actually by talking about a couple of other things and then build our way up to talking about the exciton condensation. So we're going to start our talk by talking about strong correlation problem in quantum chemistry. We're going to look at wave function theory, reduced density matrix theory, error mitigation via N representability, and talk about a novel and efficient quantum eigensolver. And then we're going to talk a bit about verifying generalized Pauli exclusion principle. And then we'll talk about exciton condensation of photons on a 53-qubit quantum computer. And then we'll wrap things up by talking about the coexistence of exciton and fermion pair condensations. And then just a few final remarks. Okay, so let's get started actually. So just a little bit of background. So again, we work in the area of quantum chemistry and many electron quantum mechanics. And let's just start actually with some very basic ideas of the representation of quantum mechanics. So essentially, on the left here, we have the classical computer. And of course, the classical computer works by encoding information as ones and zeros, as we all know, in terms of bits. And I think we often hear about the quantum computer in terms of course, qubits, where ones and zeros are entangled together, and the qubits obviously being an important generalization of the bits. When it comes to quantum mechanics, I would say another aspect of the difference, which is probably the most important, is that on a classical computer, we have really an abstract representation of quantum mechanics in terms of vectors and matrices. Whereas on a quantum computer, we have an experimental representation of quantum mechanics in terms of prepared quantum states. And it's actually this distinction that really drives the advantage, the potential advantage of quantum computing. So in this talk, we'll talk about some of the advantages of an experimental representation. So again, the key aspect, of course, is that on the quantum computer, we're not just representing the abstract information in quantum mechanics as vectors and matrices, but we're actually preparing those states on the quantum computer. So in the strong electron correlation problem, one of the difficulties is that we need to solve the Schrodinger equation for, let's say, very complicated materials that can show long-range order and other exponentially scaling phenomena in the wave function. And the traditional approach we take, of course, is to take our Hamiltonian, write down a Schrodinger equation with that Hamiltonian, solve for the wave function psi, and then from that many electron wave function, which can have many electrons, we extract essentially one or two body observables from that. And unfortunately, the process of computing the wave function is where we have an exponential bottleneck. So a scaling essentially on the classical computer that scales exponentially with the size of our quantum system. And the quantum computer then offers essentially a different approach where instead of actually computing the wave function, we're preparing the wave function on the quantum computer. And because essentially of the ability to entangle the qubits and the bits into qubits, we're able to represent an entangled quantum state on the quantum computer in a way that does not scale exponentially with essentially the size of the quantum system that we're studying, the quantum material or molecule. So in principle, quantum computing could essentially allow us to take a Hamiltonian, write down a Schrodinger equation, prepare a wave function on the quantum computer, and then abstract observables at a computational cost that does not scale exponentially. So the traditional approach on quantum computers is to think about the wave function. And in wave mechanics, we have our traditional expression for the energy as an expectation value of the Hamiltonian involving the wave function. Here we have a molecular Hamiltonian involving n electrons with the one-body kinetic energy and nuclear electron attraction terms. Here we have the electron-electron, the two-body repulsion terms. And typically we prepare the wave function on the quantum computer and measure the energy. Probably the most popular way of essentially solving the eigenvalue equation is to use the variational quantum eigensolver developed by Spiro-Gusick in 2014. And the idea basically is that it's essentially porting the idea of the Rayleigh-Ritz variational principle, where we essentially optimize a wave function, a trial wave function, subject to certain parameters, to a quantum computer. So essentially parameters in the wave function are varied to minimize the energy. Okay, so basically that's the background there. Now, one of the difficulties, of course, that we heard in the previous talk as well is that near-term quantum computers, of course, have lots of errors due to noise, and therefore the energies we compute in quantum systems to study quantum chemistry in materials will have errors. So what can we do to improve this type of situation? What can we do? Well, one approach forward is to think a little bit about reduced density matrix theory and to develop a reduced density matrix theory on quantum computers. So on our left, we have wave mechanics, where we have the energy as a functional, the wave function. And on the right, we have reduced density matrix or RDM mechanics, where the energy starts off as a functional of the wave function. However, we replace the Hamiltonian by an effective two-body Hamiltonian without changing the expectation value, because the two-body Hamiltonian, essentially the Hamiltonian itself has only two-body interactions. So we can actually just rescale that Hamiltonian so that our Hamiltonian depends only on two electrons. We can integrate over all the electrons except for two of them inside, okay, moving that inside K2. And now integrate psi star over all the electrons except for two. Okay, and that defines what we call the two-electron reduced density matrix. So the energy becomes a linear functional of our two-electron reduced density matrix, D2, and our two-electron reduced Hamiltonian, K2. So in RDM mechanics, we essentially have simplified things down where now we write the wave function in terms of the two RDM. So one question, of course, is, well, how would we implement RDM mechanics on the quantum computer? Well, basically, we can measure the two RDM from the wave function and then compute the energy. So why could there be an advantage here? Well, in terms of thinking about reduced density matrix theory, one of the things is that actually it turns out that not every two-electron density matrix actually represents a wave function. So a two-electron density matrix needs additional constraints on it, additional conditions, to ensure that it actually represents an n-electron quantum system. And these constraints or representability conditions are called the n-representability conditions, okay, because we essentially want to represent the n-electron quantum system in terms of just the two-electron reduced density matrix. And these conditions are very strong and powerful. To give an idea, if the entire set of 2 electron density matrices is both the blue and the red, then essentially the set of 2 electron reduced density matrices that are n representable would be just the blue, okay, that actually correspond to n electron wave functions or density matrices. And the n representability conditions are essentially the boundary conditions sort of in a hyperdimensional space that separates the red region from the blue region. Okay, now why is this useful for quantum computing? Because on some level, one would say, well, if we can prepare the wave function of the quantum computer, then perhaps we obviously should be representable. But the key basically is that we can actually use the unrepresentability conditions to mitigate some of the important errors that are developing on the quantum computer in the 2RDM. Okay, so indeed we're extracting the 2RDM from a wave function on the quantum computer. However, the entire process of preparing the wave function and essentially measuring the 2RDM, of course, will introduce errors. And we can use, in principle, the unrepresentability conditions as a physically motivated error mitigation or error correction on the quantum computer. Okay, let's try it. Let's take a look and see how this works. Okay, so here's a picture of one of the IBM Quantum Experience computers. So it's, of course, it's in one of the IBM computers using superconducting qubit technology. And we're going to go ahead basically and look at the dissociation of H3 on a 5-qubit IBM quantum computer. And what we see here basically is the blue represents the energy computed classically using a method called full configuration interaction, which is where we just solve the Schrodinger equation in a certain finite basis set to full precision. Okay, so here's our potential energy curve in blue. And you can see these X dots here represent the calculations on the IBM quantum computer. And you can see that to all visual effect here, we're essentially tracking the full CI, both actually in the region around equilibrium, as well as in the dissociation region. And it's important that actually as we pull the H3 chain apart, so we're actually just pulling all the bonds equally, okay, it's a hydrogen chain. We're just pulling that chain apart where everything just equally pulls apart at once. As we essentially end up in the dissociation region, the electrons on each hydrogen become highly entangled. And so we actually have some strong correlation in this region. And yet the quantum computer is basically oblivious to that, producing an accuracy essentially 1/10 of kilocalorie per mole, which is about 1/10 of chemical accuracy in this basis set, at least throughout the potential energy curve. Okay, so we're basically able to treat strong electron correlation as we essentially pull this chain apart. And the reason we're able to actually end up with such good accuracy here is because along the way, we're essentially using the unrepresentability conditions to correct the 2RDM that's being computed on the quantum computer. Okay, so it's an RDM quantum computing algorithm that essentially then allows us to use the unrepresentability as error mitigation. And you can see the mitigation works not just for the energy, but also for properties as well. So here, for example, we're looking at the sum of squares of the off-diagonal elements of the 1 electron density matrix in the atomic orbital basis. And that gives us a measure of essentially how localized the system is. And here is a function of the separation. So initially, the system is highly delocalized, representing a metal. And then as we pull the chain apart, the electron densities become localized, okay, on the quantum computer with the full CI, and showing essentially a metal to insulator transition. However, you can see as it goes down to 0, everything is isolated. Whereas Hartree-Fock theory, which is the mean field theory in quantum theory, electron theory, pretty much shows a metal the entire way. Okay, so it is the strong correlation that drives the localization of the electron density and essentially the metal to insulator transition. So we're able to see this transition in H3, which cannot be described without strong electron correlation. So in addition to that, we'd like to essentially look and see, can we develop, for example, based on some of the ideas in reduced density matrix theory, can we also go ahead, and those calculations we just presented were using a variational quantum eigensolver. But can we come up with essentially other quantum solvers that could potentially be more efficient for molecular simulations? So we recently developed a quantum solver of contracted eigenvalue equations for scalable molecular simulations. Existing methodologies using phase estimation or variational algorithms have drawbacks such as deep circuits or high dimensional classical optimization. In particular, the variational quantum eigensolver often is used with derivative-free optimization that works well for small numbers of electrons, but essentially will become intractable as the size of the quantum computer, as the size of the quantum system being simulated on the computer grows larger. So we'd like to be able to deal with some of those challenges. So one idea is we introduce a quantum solver of contracted eigenvalue equations, which is the quantum analog of classical methods for the energies and reduced density matrices of grounds and excited states by solving essentially something called the contracted Schrodinger equation. So the solver does not require deep circuits or difficult classical optimization, and it achieves an exponential speedup of the exact classical algorithms. Okay, so how does this exactly work? And let's take some examples. So in particular, we're going to solve something called the contracted Schrodinger equation, or the anti-Hermitian contracted Schrodinger equation. Physically, this is a projection of the Schrodinger equation onto the space of two electrons, and we're taking its anti-Hermitian part. Now, why is this equation so important? Well, the equation is very important for a couple of different reasons. So it basically represents the Schrodinger equation on the space of two electrons. So it's sort of the equivalent, just as the Schrodinger equation is the engine for solving for wave functions, the contracted Schrodinger equation and the anti-Hermitian part can be viewed as the engine for solving for the two electron reduced density matrix. And we can solve the ACSE by a series of two-body unitary transformations, which are shown here. Okay, so we iteratively apply a series of two-body unitary transformations to the wave function to produce another wave function at the n+1th iteration. And an important part of this is if we look at the energy as a function of these two-body iterations, two-body unitary transformations, we find that the gradient and the energy with respect to this driving transformation is this quantity here, which we can see is actually just minus the residual of the ACSE. So actually, the contracted Schrodinger equation, or the anti-ACSE, is really critical because it actually represents its residual, or its deviation from zero, actually represents the direction to minimize the energy as a function of these two-body unitary transformations. So as we follow this gradient downhill, eventually when it goes to zero, the residual will go to zero, and that'll correspond to a solution of the ACSE as this equation is set to zero. Okay, so let's sort of take a look at the algorithm briefly, and then we'll look at an example to get a better physical feel for what we're doing here. So the quantum ACSE algorithm for 2RDM optimization, here's kind of just a formal sketch. And what's important is we can actually prepare an auxiliary variable, a wave function called lambda. And when we prepare lambda, from lambda, we can actually measure it using quantum tomography on the computer, and taking the imaginary part ends up giving us the gradient information. So what's very important about the algorithm is we don't need derivative-free optimization. We can directly extract the gradient at each step of the algorithm. Then we apply that transformation, that unitary transformation, to the wave function and produce psi of n+1. From that, we can do tomography and extract the 2RDM. And then we just repeat these steps over and over until we reach convergence in the system. At each step, obtaining the gradient that we need for the optimization. In terms of advantages, so essentially it's the classical ACSE, or the ACSE algorithm for conventional or classical computers, ported over to the quantum computer. The classical algorithm actually also has polynomial scaling, but it basically requires a reconstruction of higher reduced density matrices from lower ones. And that approximation essentially introduces error. Whereas on the quantum computer, we're actually able to achieve the polynomial scaling and do it in a way that's in principle exact. It's exact up to the noise, essentially, on the quantum computer. Okay, so our algorithm is essentially exact up to the noise on the quantum computer. So let's take a look at a couple of examples. So we'll actually start off with just a really simple example. And this is fun because this is on a 1-qubit quantum computer called IBM ARMUNC. And what we're going to do basically is we're just going to optimize this 1-qubit Hamiltonian. We're on the block sphere here. This blue vector represents the ground state of the Hamiltonian. So this point on the block sphere is the solution that we want to achieve. And we're going to start with an initial point up here at the top, okay, at the top of the plus C direction. And we essentially take a gradient direction down, and you can see our first iteration takes us here. And essentially what we're doing is we're rotating by these transformations. As we solve the ACSE, each iteration is rotating us around the block sphere, okay? And as we rotate along the block sphere, in about 9 iterations, we essentially converge to the ground state of the Hamiltonian, which is right here on the block sphere. So essentially our algorithm for solving the ACSE corresponds to performing a series of two-body rotations. Okay, in this case, because we're in 3 dimensions, we can look at it as a rotation in 3-dimensional space. But if we're essentially in higher dimensions, we have a rotation in a hyperdimensional space. So let's take a look at a more challenging molecular case. Okay, so here's a case that Scott Smart and I developed on the quantum computer for looking at H2 on a 5-qubit quantum computer. We're using our ENS, the IBM computer, 5-qubit. And here's the full CI is in black down here. So this is the sort of the exact reference value. And in red, we have essentially a quantum simulation of the solution. And you can see we just sort of march right down here, and we essentially converge to the exact solution. Now, performing it on the quantum computer, of course, we have some error. So we march down here, and then essentially in about 9 or so iterations, we stabilize at about this value. So indeed, we stabilize at a value that does have a difference from the exact solution. Again, all of this is due to quantum noise. And here we can extract the potential energy curve, okay, for pulling apart the hydrogen molecule. And you can see that our full CI is here. And we have the quantum simulation in red here. And then on the quantum computer, we have the blue curve. Now, what's important basically is we're essentially doing this in a way that is essentially not using any special symmetry. So we're essentially using kind of all the traditional mappings of the fermion system onto the quantum computer. And so doing it in the most general way possible is what's introducing, to some extent, some of the error here because of the large numbers of gates. But the result basically is showing, and importantly, that even as we essentially pull apart the chemical bond, both at equilibrium and bond breaking, we're getting an accurate representation of the information. Now here on a quantum simulator, we went back and looked at breaking apart the H3 molecule. And what we see basically as a function of pulling this apart, again, this becomes more strongly correlated. So if we solve the ACSE classically, you can see here in red that essentially we shoot right up above chemical accuracy as we pull this apart. Whereas essentially the blue, which is the quantum algorithm for the ACSE, essentially is it's basically exact. This is just the degree of convergence. We converged it to 10 to the minus 10. And so we ended up with 10 to the minus 10 accuracy throughout the bond breaking. Okay, so in principle, as we essentially remove some of the error in the quantum computer, we can actually recover essentially strong correlation regions equally well as the less correlated regions by solving the ACSE on the quantum computer with significant advantages over the classical solution. Okay, so before we get to the exciton condensation, okay, which will be a good test of some of our ideas for a more complicated molecular material, I want to talk about an experiment that we did on one of the IBM quantum computers to investigate essentially the validity of an n-representability condition. So indeed, n-representability, the idea that we need conditions to constrain the reduced density matrices to represent the many electron quantum system, it's a bit of an abstract notion, and it's something that's always been theoretically developed, but basically there's never been a really simple way of actually demonstrating an n-representability condition experimentally. And so we realized there was an opportunity to do that using a quantum computer. And so we ended up picking a special set of n-representability conditions, which are called generalized Pauli constraints. And so basically what they are is a generalization of the Pauli exclusion principle. So probably many of us are familiar from sort of introductory chemistry that the Pauli exclusion principle tells us that the orbital occupations must lie between 0 and 1. Okay, so what does that mean? Well, basically, obviously the orbital cannot be less than filled, and it obviously can't have more than 1 electron because essentially the electrons are fermions. But is that actually the entire story? It turns out there's a generalized Pauli exclusion principle that for wave functions with more than 3 electrons, there are additional constraints. Okay, so if you actually have a pure quantum system for 3 or more electrons, it actually turns out the Pauli exclusion principle is not the whole story. And so these generalized Pauli constraints can be viewed as a class of n-representability conditions on reduced density matrices. Okay, so in fact, the Pauli exclusion principle itself is an n-representability condition, and these generalizations give us more. And so the experiment that we'd like to do is to verify the generalized Pauli constraints experimentally. To do that, we're going to prepare and measure a random sampling of quantum states on IBM's quantum experience. Okay, so basically the idea is to just use a series of unitary transformations that can actually drive us anywhere, essentially, in the space of 3 electrons. Okay, so we basically have our 3 electron wave function. We have a series of rotations and C0 gates and a couple of different angles here, alpha, beta, and gamma. And we're going to use that to sort of move around all different parts of our 3 electron wave function. And here are some results then. The occupation numbers, it turns out the occupation numbers for our 3 electron system can actually forms a 3-dimensional polytope. It's 3-dimensional and not 6-dimensional because 3 of the occupation numbers are redundant with the other 3. So if we have 3 electrons and 6 orbitals, we actually only need 3 orbitals to represent the information. So we end up with this nice 3-dimensional polytope. And it turns out, so this polytope, I'm giving it 2 different colors. We've ordered the occupation numbers from largest to smallest. And so because of that folding, the Pauli exclusion principle actually ends up being this entire object. Now, if the generalized Pauli constraint is true, if there are generalized Pauli conditions, then there's an additional constraint, this hyperplane in green, separating sort of the yellow region in the front, the yellow-greenish region in the front, from the purple-blue region in the back. And this hyperplane basically separates the allowed region in the front from the forbidden region in the back. So the back is forbidden because it violates the generalized Pauli constraint that's been derived theoretically. Interestingly, the constraint was actually derived theoretically, actually computationally motivated for the first time in 1971 by 2 scientists, Borland and Dennis, who were actually working at IBM, and they were doing quantum chemistry at IBM, and they were doing some calculations, and in the process, they recognized that there were certain additional constraints beyond the Pauli constraints that essentially were never violated when performing full configuration interaction calculations. So it's kind of exciting that basically many years later, here we are with an IBM quantum computer, and we're going to now test whether the quantum computer agrees that these conditions are essentially, if we actually look at it experimentally, do we verify that these conditions really exist? Okay, so again, the quantum computer is an experiment. So we're going to go ahead and do the experiment and check this out. Again, this boundary is the boundary between the allowed and forbidden region. Okay, so let's go and see what happens. So we're going to basically suppose, for example, if both regions were allowed, okay, then by random sampling of 60 states, about half should lie on one side of the condition and about half should lie in the forbidden region. It's kind of like all the air in the room, you know, wouldn't just go to one side of the room. The probability of that is minuscule, so we don't have to worry about, you know, essentially any kind of catastrophic event there. And so in the same way here, if we randomly prepare the states, they should lie on both sides. If the constraint is not true, but they should lie only on one side if we actually have the constraint. So voila, here's the results from the quantum computer. We find that all of the randomly prepared states lie in the yellow region. So the result verifies the generalized Pauli constraint to 1 part in 1 quintillion. So 2 to the 60th is about 1 in 1 quintillion, essentially showing that indeed the theoretical ideas that motivate generalized Pauli constraints do hold up when we essentially perform the simulation on the quantum computer, and that these conditions indeed are shaping the quantum reality that we have, providing supports and hyperplanes that shape where we can essentially drive our quantum system. And these constraints become more numerous as we go beyond 3 electrons and more complex, of course, as well, but are very important for shaping the landscape of what quantum theory can do. Okay, so this now brings us to the next part of our talk, where we're going to talk a little bit about something called exciton condensation. And to motivate what is exciton condensation, I'm going to back up a little bit and talk a bit historically about condensation phenomena and how that has led to some really recent and exciting research in the area of something called exciton condensation. So let's start off with Bose-Einstein condensation. So we go back to the work of Bose, 1924, deriving photon gas statistics. The work of Albert Einstein, also in 1924, applying the statistics to particles with arbitrary mass. And then the very important paper by Fritz London called On the Bose-Einstein Condensation from 1938. And so basically London recognized that these bosons and their statistics would allow essentially any number of such particles called bosons to essentially condense into the same quantum state, into the same orbital. Okay, and so bosons basically violate the Pauli exclusion principle, and we can have any number we want in the same orbital. So from an electronic or fermionic point of view, it does seem strange, but pretty amazing that essentially we have these two classes of particles, fermions and bosons, where the bosons can essentially act so differently just from a difference in statistics. Okay, so it was also recognized by Zitze in 1947. And then in 1940, we had the connection between spin and statistics from Wolfgang Pauli. Okay, so historically, you might think, well, this is something then that should have been experimentally realized early on. However, kind of the early liquid helium experiments didn't really show pure Bose-Einstein condensation because there was no way to separate the attractive forces in the helium gas from the statistics. And so when condensation was observed, it was being driven not just by the statistics, the Bose-Einstein statistics, but also by the attractive forces. So it wasn't actually until the 1990s that BEC was realized in its pure form by using essentially very dilute gases of alkali metals. Okay, so basically the first realizations were done in 1995 in rubidium and sodium metals by Cornell Veeman at Gila and Ketterle at MIT, using rubidium and sodium respectively. And so here we can actually see a picture of the peak emerging. So the idea is you basically pour kind of like cool down using evaporative cooling and basically a magnetic trap. We essentially cool the quantum particles down. They go into the quantum well, and we end up getting our Bose-Einstein condensation. So I'm always excited. Bose-Einstein condensation for me is also very kind of like just exciting in my own formation as a student. I was a graduate student at Harvard shortly after this experiment. And I do remember Wolfgang Ketterle coming to Harvard to give a talk, and just the excitement of just seeing how he had used essentially fundamental science to just, spectroscopic techniques to really visualize something just so fundamental as these statistics in the particles. And also at the time, my roommate, Dave Landis, who is actually now at Google working on quantum computing, was working with Kleppner over at MIT. And Kleppner was pursuing essentially Bose-Einstein condensation in hydrogen atoms. And I still remember just it took months and years of work to essentially get that to work. And I think it was 1998 or 99 when it, finally was realized in the atomic hydrogen. And I just remember Dave Landis coming home and the excitement of essentially realizing Bose-Einstein condensation in his lab with the hydrogen atoms. Okay, so back to our story here. So of course, Bose-Einstein condensation is sort of the quintessential condensation phenomena. We also, of course, know superconductivity is also a condensation phenomena. Here we have the Meissner effect observed by Meissner and Oschenfeld in 1933. Basically later determined to basically be electron pairing. So electrons, of course, we know we can't put more than one electron in a spin orbital. However, we can actually put many electrons into essentially a global quantum state by pairing the electrons to form essentially quasi-bosons. Okay. And the theory of superconductivity was developed by Bardeen, Cooper, and Schrieffer in 1957. Here we see phonons mediating the Cooper pairing. Okay, and so that's the basic idea of the BCS theory for superconductivity. And we, of course, can also have high temperature superconductors, which also function by Cooper pairing, even if the exact mechanism is different from the BEC phonon-induced mechanisms. We can have iron-based superconductors, okay, with temperatures around 55 Kelvin, or copper oxide superconductors, like the ones here on the right. And again, in these high temperature superconductivities, the standard theory does not apply, okay, but we still have Cooper pairing. And here you can kind of see as a function of the critical temperature for superconductivity as a function of time, how we've been able to achieve superconductors at higher temperatures, the important work in the mid-80s, which led to the whole family of the copper oxide family here, reaching higher temperatures. And we also see the important iron family, okay, in the mid-2000s. Also point out the hydrogen sulfide here at very high pressures at 155 gigapascals. Okay, so basically we've seen Bose-Einstein condensation of bosons. We see essentially a kind of condensation of fermion pairs to form superfluids, superconductors. But what about a Bose-Einstein condensation of something called excitons? So this idea was first put forward by Blatt, Boer, and Brandt in 1962, or at least this is one of the very earliest papers to look at this. And one question is, well, why do we care about this phenomenon? First of all, what exactly is going on with excitons here, and why do we care? Okay, well, basically excitons are particle hole pairs. So an exciton is formed, for example, if we take a fermion and we pair it with the hole, the absence of a fermion, then essentially they can pair together to form an exciton. And it turns out we can take a large number of excitons and we can condense them at low enough temperatures in certain materials to essentially create, in principle, a exciton condensation. And we obviously know that superconductivity is important because it leads to essentially friction-free flow of electrons. But it turns out the analog for energy is actually exciton condensation. So exciton condensation leads to a frictionless flow of energy, first recognized in principle by Keldysh in 1968. Okay, so for example, if we have electrons flowing from left to right on the top here, we could have essentially then the holes have to flow from left to right, meaning particles now flow the opposite direction. And so if we induce a current on the top, we essentially get a current in the opposite direction for free on the bottom. Okay, and so, and essentially it's showing here that how we essentially have a friction-free flow of these excitons in the material. So it turns out, though, exciton condensation historically was very hard to achieve. It was only achieved in the early 2000s by essentially using strong magnetic fields or strong interactions with light in polaritons. So here you can see using the B field on essentially 2 graphene layers. So we take 2 layers of graphene, we match them, we put a strong B field, and the particles in one layer line up with the holes in the other layer in a checkerboard-like fashion. And then essentially people were able to measure, scientists were able to measure the maximum interlayer tunneling conductance. So essentially at sort of the zero bias voltage here, they're able to get DI/dV to have a strong peak, showing essentially sort of a friction-free flow of electrons through those 2 layers, implying the exciton condensation. Now my research group got interested in exciton condensation with this paper, which appeared in Physics Viewpoint, one of APS's publications, and it was called Chasing the Exciton Condensate. And in 2016, when this came out, the exciton condensation had still not been realized without strong B fields in any material. However, some new signs were emerging that might happen soon. And so indeed, actually, we got interested, started working on it theoretically, and then essentially in 2017, basically exciting news out of Harvard, where Halperin and Kim announced essentially achieving exciton condensation in graphene bilayers for the first time without strong magnetic fields. And they also found that the exciton condensation was extremely robust to essentially changes in geometry and modifications of the material. Okay, later in 2017, we also had exciting work from Abamonte at the University of Illinois. He announced in Science signatures of exciton condensation in a transition metal dichalcogenide. So here we have a picture of this transition metal complex. And indeed, it basically involves molybdenum, tungsten, titanium. And basically, they were able to use momentum-resolved electron loss spectroscopy to essentially confirm the existence of the exciton condensation around 180 Kelvin. Very recently, in October of 2019, there's been evidence of exciton condensation now in 2-dimensional atomic double layers. Okay, and this opens up some new possibilities to look at exciton condensation in these van der Waals heterostructures. And this was done at temperatures a little bit above 100 Kelvin. Okay, so this basically brings us to some of our research. And so one of the things we were thinking about is how do we come up with a bona fide signature for quantum condensation, exciton condensation? Well, the Bose-Einstein condensation signature is a large eigenvalue in the 1 boson reduced density matrix. So essentially, here's our one boson reduced density matrix in second quantization. It has a large eigenvalue that represents the number of bosons in a single orbital. Now, fermion pair condensation, FPC, the signature for that occurs in a large eigenvalue of the 2 fermion RDM, because we need 2 fermions, 2 electrons, to actually have the condensation. So there, the natural quantity is the 2 RDM. This was first recognized in 1962 by C.N. Yang, working at the Advanced Institute at Princeton. And we were wondering then, well, can we come up now with equivalent exciton condensation EC signature? It must be a large eigenvalue in the particle hole reduced density matrix. Okay, so my postdoc Shiva, Safi, and I recognize that basically it's the G matrix that should have a large eigenvalue associated with it. And it turns out there was some earlier work from the 1960s also recognizing in the reduced density matrix field that one could have collective excitations of bosonic systems, or collective excitations through essentially large eigenvalues of the G. But this work had been largely forgotten, and so Shiva and I were able to sort of bring it back and recognize that we should be able to use this as a powerful signature for exciton condensation. And so we got interested in looking at molecular scale exciton condensates. We took a model system of essentially taking some hydrogen atoms and putting them in a line, and then essentially taking another hydrogen chain above it, and essentially varying the distances between essentially the hydrogen atoms within a chain and the distances between the 2 chains, okay, represented by L and D respectively. And we found that if we tuned L and D to the ratio that essentially is predicted to be essentially the regime for exciton condensation in the theoretical physics literature, we indeed found in this molecular scale system, we found the emergence, the beginnings of exciton condensation. So as D goes to about 2 angstroms, we see the large eigenvalue in G go from 1, which is its value in the absence of exciton condensation. The large eigenvalue of this modified G goes up and essentially reaches a maximum around 2.5 angstroms. And so this is exciting. It's showing essentially for the first time that we can actually get exciton condensation potentially not just in large scale materials like graphene bilayers, but also essentially in smaller molecular scale systems as well. So for example, if we put a hole here at the red dot, the particle essentially ends up on the other layer across from it. Likewise, if we put a particle over here if we put a hole over here at this layer, then the particle will be over here. Put the hole over here, then the particle likewise will be over here. So indeed, the particle and holes are matched essentially in essentially the eigenfunction associated with this large eigenvalue. We can show this in more interesting systems as well. So for example, if we take hexacene, which is an acene chain, like a little patch of graphene, a linear patch, and we essentially pair it with another hexacene molecule, so we have a hexacene electron double layer, EDL, then at around 2.5 angstroms separation, we see the large eigenvalue emerge, and we see the beginnings of exciton condensation in this molecular scale system. So this got us thinking a little bit about the idea of, well, could we actually use some of these ideas to prepare an exciton condensation, exciton condensate, essentially on a quantum computer? And could we actually prepare the condensate itself as an experimental realization where we actually would have not essentially just, well, that we actually have not just a sort of an abstract representation of the exciton condensation, but to actually prepare the exciton condensate on the IBM quantum computer. Okay, so at this point, actually, I'm going to transition to LeeAnn. So LeeAnn Sager, one of my graduate students at University of Chicago, is the first author on this paper on exciton condensation on IBM's 53-qubit quantum computer. So, okay, so we're going to basically do a little trade-off here. So I'm going to go ahead and stop screen sharing for a moment. And let me just see. Okay, so I'm going to stop my share here. And I'm going to turn it over to LeeAnn to tell you a little bit about the results here that we obtained. LeeAnn, are you ready to screen share?
It's not looking like it's going to work right now. I think I need to be made host.
Oh, okay. So we're doing a little bit of a, okay, so Alexi's going to become the host, and then he's going to make you the host, and we're going to change hats here. So
Yep,
just a
there we
minute.
go.
All
Okay.
done.
Yep. All right.
Go ahead, LeeAnn. All yours. Thank you, David. It was awesome. It was great.
Thank you.
Okay, so As David was saying, we were thinking about how to prepare some excitons on the IBM quantum computers, and we noticed that the transmon qubits were basically composed of photon hole excitons. So the first thing that we did was we looked at a 3-exciton system, which we knew could show exciton condensation, and we did multiple preparations of 3 excitons using different input parameters for the preparations. So we used 3 different angles to prepare this, and we varied them all from 0 to pi/2. And for our simulated results, the graph that I'm showing you here is a heat map of what happens as you vary those parameters, specifically varying θ2 and θ3, with θ1 being set to 0. And if you recall from what David was saying, the signature of exciton condensation is that large eigenvalue in the particle hole reduced density matrix. And anything above 1 demonstrates exciton condensation. And for a system of 3 excitons, the maximum value that we can get there is n/2 or 1.5. So the simulated results here not only demonstrate exciton condensation, but they demonstrate maximal exciton condensation with an area around that maximal preparation that still demonstrates very large exciton condensation for a 3-exciton system, which was super exciting. So then the next step was to transition from simulation to running the computations on IBM's devices. Specifically, we ran experiments using IBM Yorktown for the 3-qubit 3-exciton results. And we do indeed see exciton condensation pop up on Yorktown in the region exactly where we would expect it. Again, it's rather robust region, right around that pi/2 zone. We did perform some error mitigation, but we were interested specifically in the non-mitigated results because that showed the true noisy quantum experiments, and those experiments were able to achieve exciton condensation, which showed us that we did indeed have excitons on the quantum computers. Okay, so another way to visualize our results was to go back to that the generalized polyotope that Scott used in some of his work that David was talking about earlier. So as you can see, we're still demonstrating here that we are in the allowed region, but moreover, we notice that there's a trend in how large those the signature of exciton condensation is. The darker the color, the higher the signature of exciton condensation. So when you're on that hyperplane, that Borloo-Stennis hyperplane between the allowed and not allowed region, we don't really see exciton condensation. We see like a bright red, it's right at 1, so that's not really exciton condensation. But as you get closer and closer to that 0.5, 0.5, 0.5 region, you get darker and darker, which indicates a larger exciton condensate signature. In fact, we see the largest 1.5 at that 0.5, 0.5, 0.5 vertex, which we recognize as, there are several preparations that have that 0.5, 0.5, 0.5 value, but one such preparation is the GHC state, which we'll use, I'll show you after the next slide, to extend from just 3 excitons to n excitons, we use this preparation. First, we also have these results in some experimental data. Okay, so we started just looking at 3 to 5 qubits, or 3 to 5 excitons on Yorktown, because that's what Yorktown can do. And as you can see, as you increase the number of qubits, you increase that signature of exciton condensation, which means we're getting more and more excitons condensing into that single quantum state, and almost in a linear fashion here. So in order to go to higher qubits, we also looked at data from IBM's Melbourne computer, which goes up to 15 qubits. And we're still seeing more and more exciton condensation as we go to higher and higher qubits. And then we wanted to see what happens when we go even further to higher qubits. Does it keep increasing? Do we keep getting higher and higher exciton condensation? So we looked at Rochester, which has up to 53 qubits. And indeed, we're still seeing some growth in the number of excitons that we have condensing as we increase the system size. Here's a nice little summary of all of the data that we gathered. And as you can see, even for the 53 qubits, we have demonstrated exciton condensation. So we have prepared an exciton condensate on the quantum computers, an experimental exciton condensate on the quantum computers for systems of up to 53 excitons, up to 53 qubits. Okay, so we wanted to look at why we didn't necessarily get the maximum n/2 values for the quantum computers experimental simulations. We do get exciton condensation, but it's not the maximal exciton condensation. So we thought that what might have been happening is that we were having some sort of decoherence on the devices, which didn't allow all of the qubits to become perfectly entangled with one another. So we thought, okay, let's look at all of the eigenvalues of the the particle hole RDM, that signature. Anything above 1 shows that there are multiple qubits interacting with each other. And looking at the sum of all of these values tells you kind of how many excitons are interacting with other excitons, but not necessarily all in one global state, but rather in islands of correlated states. So the way that we visualized this was to look at the sum of all of the eigenvalues above 1 versus the number of qubits. Again, the maximal exciton condensation that one would expect is that diagonal line there, the dotted diagonal line. And we're still looking at the Yorktown experiments, the Melbourne experiments, and the Rochester experiments. And as you can see, we do seem to approach that dotted line. So we are getting close to the maximal exciton condensation, but they're just in different islands of condensation, likely due to the decoherence on the quantum machine. Okay, with that, I'm going to turn back over to David for the last little bit of our talk.
Let me do the same dance with the host.
We'll do it.
1 second, so I'm getting host now, and now I will make David host. Done?
Yeah,
all yours, David?
All right, I'll come back to screen share here. Hold on a second. Okay, I'm going to do a little fast forward here. All right, right to the, hold on a second. Okay, so we're coming back to, okay, here, and we come back. Okay, so here we are. So it's a little kind of time travel forward here. So LeeAnn did an awesome job telling you about essentially the work here on the exciton condensate on the IBM quantum computer. And so one question that came up in our minds, we've been thinking theoretically about, of course, the idea that we have superconductivity has a large eigenvalue in D, and exciton condensation has a signature of a large eigenvalue in G. And we started thinking theoretically about this question. Is it possible to essentially create a material that actually would show dual fermionic and exciton condensation at the same time? So essentially a state that would actually have kind of both of them, both condensations occurring simultaneously. And so the goal is basically to computationally demonstrate the existence of a fermion exciton condensate in a molecular system. Okay, so here's obviously the fermion pair condensations, and we'd like to add that to the exciton condensation to really have both of them present at the same time in a system. Now, one question, of course, at first, we weren't even sure, is it possible to even have a large eigenvalue in both D and G at the same time? So really, when we started the project, I don't know, we weren't really sure about the answer. And so we were excited. We wanted to figure out, can we actually have both condensations? So LeeAnn basically looked at 3 electron systems, and we plotted basically the lambda, so that the axis here, the y-axis should be lambda sub d, the large eigenvalue for the D2 matrix, and the x-axis is the large eigenvalue for the G matrix. And what we see basically is all these x's represent different states that were computed for different 3-electron states that are being computed. And we're seeing essentially how those states essentially can go from the largest possible lambda d to essentially the largest possible lambda g. Now for 3 electrons, it's actually not possible to have essentially fermion pair condensation. So the lambda d does not get larger than 1. However, we can have a large eigenvalue in G, and we can see that largest eigenvalue is 1.5, which we observed earlier in the talk as well. So essentially, it turns out that as we look at different states that are allowed, we see that those states have an elliptic trade-off between essentially large d and large g. So essentially, you can kind of see here you have large d, but now essentially d gets less, but now g is getting larger. Okay, so there's an elliptic relationship between the two. And so maximum exciton condensation in this case has no fermion pair condensation. Okay, so that's the maximum exciton condensation over here. And over here, we have the maximum fermion pair condensation. But in this particular situation, we don't see any of that. Okay, so now we basically wanted to look at a 4-electron system. And in the 4-electron system, now we can see that we are getting fermion pair or kind of superconducting type condensation in the system for some states. And other states are showing the maximum exciton condensation, which is 2 in this case. But what is really interesting and exciting is that in this region here in the middle, we actually see states that actually have both a large eigenvalue in D and a large eigenvalue in G simultaneously. So these states are realizing essentially a state that has both exciton condensation and it's undergoing exciton condensation and fermion pair condensation simultaneously. Okay, so we can basically a coexistence of condensates. So again, maximum there and there, but now we essentially have this new region where we actually see states with both exciton and fermion pair condensation in the same state. So we can actually summarize this in this figure here, where down here we have no condensation phenomena. Up here we have a state of matter which is fermion pair. This is the traditional superconductors. Here we have the state of matter that's exciton condensates, which again have only recently been realized in the last few years without large magnetic fields. And now in this new purple region here, we have the prediction that we can have a coexistence or states, a new state of matter, if you will, that actually shares both essentially the properties of the fermion pair condensation, but also potentially the properties of exciton condensation. And so the state basically has both of these simultaneously. And this is just the elliptic trade-off between essentially maximum pair condensation and maximum exciton condensation. Okay, so that's the region there. And what's really important is you might wonder, well, when you actually create a quantum state that actually shows both particle, or both essentially particle-particle condensation and the exciton particle-hole condensation, are we actually just getting 2 separate condensates? And so importantly, our calculations show that actually we're not, that actually the two are actually non-trivially enmeshed. And you can see that because these squares here represent, it's a little bit of a complicated representation, but we've essentially unrolled the orbitals 1 through 8 in this direction, and we've unrolled them in this direction. And the squares represent essentially the interactions between essentially a particle in this orbital and a hole in that, or a particle in this orbital and a particle in that orbital. Whereas here, this represents a particle in this orbital, but a hole in that orbital. And so where the squares are more colored, you're essentially getting a greater contribution of that particle-particle pair or that particle-hole pair. And so just comparing squares, you can see that there are squares where you're essentially getting both particle-particle condensation and particle-hole condensation at the same points in our lattice. And that essentially shows that we're essentially getting fermion pair condensation and exciton condensation in a way that's highly enmeshed, or, if you will, entangled. And so we can actually formalize this more rigorously in the large number of particles, large N thermodynamic limit. And what we do basically is the following. We theoretically write down a model system that shows basically fermion pair condensation. And so one example of that is the anti-symmetrized geminal power model, AGP model. Those Hamiltonians and wave functions exhibit large eigenvalues that represent essentially superconductivity, Fermi-Ampere Cooper pairing. And we also can write down a model due to Lipkin that has a limit in which it shows exciton condensation. Now, we can actually do this in general while we're using these two models to kind of motivate the idea. We can actually use a wave function that exhibits these characters from any general model that shows essentially exciton condensation and Fermi-Ampere condensation. And it turns out if we take an entanglement of these two wave functions, this one showing essentially fermion AGP showing Fermi-Ampere condensation, and the wave function showing exciton condensation, if we entangle these two with the appropriate sign of entanglement, et cetera, what we can find, we can prove basically, is that this new wave function created by the entanglement, okay, is a fermion exciton condensate, and its eigenvalue in D is actually bounded, okay, it's always greater than or equal to this relationship here, which is equal to n/2 minus the square root of n. So for large n, we can see that the large eigenvalue of D for this new wave function is going to be essentially a large eigenvalue. Likewise, the maximum eigenvalue of G has to be greater than essentially n/4 minus the square root of n/2. So therefore, as n gets large, this also has to have a large eigenvalue. So basically, we have a proof that entangling essentially a wave function that exhibits Fermi-Ampere condensation with one that exhibits exciton condensation produces a new wave function that actually will have both condensations at the same time. So that's exciting because it shows basically we can generate a very large family of quantum states that actually exhibit both Fermi-Ampere and exciton condensation. And this new state of matter has the potential to have properties that are associated historically both with superconductors and exciton condensates. So in principle, we can generate materials that have an efficient flow of not just electrons, not just superconducting in terms of electrons, but also superconducting in terms of energy. Okay, so that pretty much brings us to the end of the talk. So just want to acknowledge everyone in the research group here. So a picture of the group. I want to, in particular, highlight Scott Smart, who's over here on the right. So Scott basically had a hand in all the work you've heard today on the quantum computing. He's been doing just some fabulous work on quantum computing, all different aspects of things. And Scott's been involved in all of the coding and all the details. So a lot of the work I talked about, all the work really I talked about today, Scott was instrumental in doing all of that. And none of it could have been possible without Scott's work on all that. So the two of us have been partners in all this. And LeeAnn Sager. So LeeAnn just talked a little bit ago, and LeeAnn basically was involved in all the work on the exciton condensates on the 53-qubit quantum computer, as well as the research of showing that we can have potential coexistence of excitons and Fermi-Ampere condensation as well. And I also want to highlight Shiva Safi. Shiva was involved with me on the work showing that we can actually use large eigenvalues in the particle hole G matrix as a signature for exciton condensation. Finally, a big thanks to IBM Quantum Experience. We couldn't have done the 53-qubit calculations without Sebastian's help getting access to Rochester, and it was really exciting to be able to run calculations on that and see the emergence of the exciton condensation. A thanks to DOE, NSF, and ARO. And finally, a big thanks to everybody tuning in today. I really appreciate this new series is exciting, and it's been a real pleasure to present today and discuss our research. All right, thank you.
Thank you, David and LeeAnn. We have time for questions, so folks, feel free to just go and ask your questions directly, and David and LeeAnn can answer.
Hi, can I ask a question directed, I think, mostly towards LeeAnn about the difference between the different machines that you saw? So when I was looking at your plot, I could just about believe that the Rochester and the Melbourne series were the same series. and then it seemed to drop down quite a lot when you switched to Rochester.
Mm-hmm.
Is there some feature of these devices that could explain the difference?
Well, the connectivity is, yeah, the connectivity is a lot different between all three devices, as well as the error rates, especially the CNOT errors. So they probably just had differences in the decoherence that was happening in the GHZ state.
So I would have expected Rochester to have better decoherence since it's a newer machine compared to the other two. I don't have the numbers on hand.
I have the numbers in the SI for the paper that we have out on this. It might be beneficial to look at those, but I do believe that Rochester has higher error values.
Okay, thanks.
Other questions? Going once, going twice. If not, let's thank David and LeeAnn for the great talk. Now we have an interesting part. So we still have, I want to thank, we have more than 30 people. I think at peak, we had about 57. And actually, it's interesting. A lot of folks sign up, during the night on my time, some daytime, European time. So people still sign up substantially. During the first part, we had about 20 sign-ups. So we had about 75 sign-ups from all around the world. So I want to thank everybody. We tried to follow up with emails, put the Zoom link right on the website, so a lot of people just joined us. So thanks, guys. So now we have a very interesting part I wanted to share with you, what we wanted to do. This is very typical in computer science conferences now, where we have a lot of topics and a lot of people. So what we do, we basically create a spreadsheet. It's called Unconference, so people just propose talks. And this is a good way for the group to self-organize, make the most use of their time by seeing the talks. Then we let everybody who proposed the talks in the spreadsheet pitch it for a minute. And then we vote if the number of talks exceeds the number of available time slots, or if it's a physical conference, you can have venues, right? You can have rooms. You basically, schedule talks onto rooms. We actually had 2 sign-ups for the lightning talks. We call them lightning with a short, following the main program. I think we just can let folks tell us what they're going to talk about, and then we can go into the talks. It's up to you guys to stay, obviously. I want to see if John Candelaria and Terrell are both here. If you guys are here, if you can say so. Mute yourself if you're on mute. I see John is here.
Yes, this is John.
Yes, and Terrell, are you here? Not sure if Terrell's still here. So we'll see. So John proposed a talk entitled QEDC Workforce TAC, Introduction to the QEDC Quantum Workforce Development Committee Activities. So I think we'll just let you share. Do you have slides? Should I make a host for presentation?
Yes, I just have a couple of slides that I wanted to go through.
Okay, sounds good. So let me make a host, and then please introduce yourself for the folks who. Let me see. 1 second. I'll need to see if I can do that. Okay, yeah, I need to reclaim host first. Now I do that. I make a host. Yeah, please introduce yourself again for those who join us later. And the floor is yours.
Okay, well, thank you very much, Alexia. I appreciate this. This is a great event. I learned a lot today, so appreciate that. My name is John Candelaria. I work at Stanford, and we also are doing quite a bit of quantum research there, as you know, and I'm leading a program that is funding that research with funds from industry. But I wanted to talk today very briefly about another activity that I'm involved in called the Quantum Economic Development Consortia. So this is a consortia that was formed in the US under the National Quantum Initiative that was started a couple of years ago. It is a consortia that is made up primarily of member companies, but it has a very broad charter. The charter is essentially to identify and develop strategies, that's here, to address the gaps in the enabling technologies and supply chain. As all of you know, there's a lot of work to be done in developing the supply chain for the hardware that's involved in quantum computing, as well as communications and sensing. We're also chartered to start developing some performance metrics, trying getting people together and agreeing on what the common benchmark should be in all of these quantum areas. And lastly, the part that I'm most directly involved in is developing the workforce. So trying to connect industry with academia and as well as government agencies in order to provide curriculum development advice to universities and get the connection made to industry and what their needs are and skill sets that are needed. So there are advisory committees that I invite all of you to take a look at and join. It's open to anyone, whether they're in academia, national labs, or industry. These are the technical advisory committees. There's one looking at use cases. There's one that's looking at the enabling technologies, performance and metrics, and the workforce committee that I mentioned before that's, again, developing curricula in universities. These are the signees. These are the companies. There's almost 150 signees now in companies in all different aspects of computing, sensing, and communications. There's a number of universities, academic institutions that are also members, and other national labs that are also participating. So for anyone who is interested in getting more information about this, they can contact me, John Candelaria at Stanford, or they can contact the two leads of this consortia, Joe Braj, who is the director, and Celia Merzbacher, who is the co-director of this consortia. And here's the address for the organization, the quantumconsortia.org, and you can learn a lot more about it there. But again, I urge you, if you're interested in participating, we are looking for people to contribute ideas to technical roadmaps for the technologies in computing, communications, and sensing, and also ideas that they might have about benchmarks and how to develop the benchmarks, common benchmarks that we can use across all of the research areas and entities that are participating around the world in this space. So again, it's a great activity. It's critically important, and I hope to have as many of you as possible consider joining this effort. Thank you.
Thank you, Jonathan. Does anybody have questions for Jonathan about the consortium? I think it's a great development and certainly brings people together. So we really love to ally, with other communities and create kind of a hub where multiple communities can share what they're doing. So this is great. Any questions for John? Can I ask you, John, my own question? So is when you say the workforce, so is the idea basically to raise talent, to basically track education and tailor kind of programs encouraging students to learn subjects which are then make them hireable by the industry partners and they will collaborate? Is that the idea?
Yes, that's exactly one of our key goals, especially in the workforce committee that I'm leading right now. So yes, we want to get a two-way conversation going between industry and academia, for instance, in order to help academia develop new curricula in the quantum area that will feed directly into industry, and again, industry obviously making direct connections with the students and the faculty to fund their research while they're still in universities.
Interesting. So for instance, right now, a lot of students are looking for summer internships.
Yes.
Is there a resource on your website where potential, collaborators, students can look for internships, graduating PhD candidates can find jobs? Is this the hub? Where is it already up there? How do they find the jobs and internships?
Yes, well, I'm glad that you asked that question, actually, because we're in the process now of adding that to our website. So there's going to be a place there for a two-way connection. So members of the consortia will be able to advertise their internships and job openings, and students can go there, as well as we're also going to be following that up very shortly with a site where students can upload their resumes so that the members can actually search the resumes using the same website. So that one will probably be coming within the next month or so, but probably within the next couple of weeks, we will have the site available where members can advertise their job openings. And again, this is the address.
Got it. Great. Now, I actually receive already, inquiries from students around the world, and so that would be great. If you would like us to share using, our website and mailing list, we'd be happy to do so. So it's great. So thanks for sharing this. And if anybody knows folks, especially students, I think now who are looking for internships, this is a great place to direct them to.
Right. Well, thank you very much.
Absolutely. Thank you, John. Let's see. I'm not sure we have others. Does anybody else want to use the floor for announcements, for discussions? I think we have some time. We have about 20 folks left. Feel free to say, what you think about this format. What would you like to see? We'll share a feedback form with brief question, how did we do? What was good? What can be improved? So please, when you get this email, please spend a few minutes, or maybe 1 minute, less than a minute, to share your feedback with us. So now it's basically, it's all yours. The floor is open for anybody. You can ask questions. So what we had an interesting topic. We had talk solicitation. So you instead of giving a talk, you may ask for a talk. Maybe for the future series, we'd like to invite speakers. So if folks want to learn a topic, or they want, for instance, a more one-on-one introductory talks to an area which is not your primary area, that's also one way to use this format. So you can ask, basically, teach me X. So anybody, feel free to unmute yourself and say anything you'd like. I know it's been a while, so I'm not sure how,
yeah, hi, this is Balaji here. I would like to know the current situation, COVID-19, how quantum computing is helping to find solutions for that. What are the research done in that zone?
This is a question for anybody. I mean, I see for sure that people are at home. That is clear, and I understand that remote access is possible. So that part, I think, is unimpeded. Can anybody talk to any COVID-19 implications? I guess not. So, but it's a good question. So we'll make a point of sharing this question, because I think it's every community got together to help the fight against COVID-19. I think there is a lot of modeling going on right now in the conventional big data AI space, pharma. I know personally, for instance, Databricks, the Spark company, they have a health science vertical, right? So which was, I think, previously doing protein folding for pharma, and I think they're kind of making it available for vaccine. I don't know what the quantum state of practical application there is. So if anybody knows, please share it with us. Balaji will forward it to you if we find out. Thank you for the question.
Thank you.
Any other questions?
Oh, one thing I was going to suggest, I think it'd be fun if we could have some interactive sessions, because we all have probably computers too in front of us, and we learned about the PyZX package and whatnot, and I think it'd be kind of fun to follow along with some sorts of applications.
So you're talking like a hands-on tutorial for
yeah.
physics. Aleks, I see Aleks is still here. Aleks, can anybody from your group basically just lead the class and we all learn and hands on keyboards and you can grade it if you like?
What was the question again?
The question is, Emily wants to basically, for you to teach a class on physics as a structured tutorial. Maybe if you have a Jupyter notebook, people can follow, right, and learn by doing. I'm a huge fan of this, right?
Yeah, I think it'd just be fun to have more things like that right now, since we all have our computers with us and whatnot.
Yeah, I think it's a good idea. Maybe we could also get somebody. Ross is left from now, but I think you can also get access to Ticket and maybe somebody from the Qiskit team to do something like that. I think would be quite cool. Maybe we could organize a few of them kind of as quite short things in a row in a block or something like that.
Mm-hmm. That's a great idea. I'll take it as actually a point for maybe the next one, right? Because we want to do this monthly. So now folks are all at home, stuck with computers all the time. So if people have prepared tutorials, we can just indeed, sequence them maybe half an hour each, right? And just do them boom, 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 one after the other. And so everybody can get kind of an overview of tooling and learn. Awesome. I'll try to set it up. And also, guys, if you have an idea for a talk going on, my mail is on the site. So just email me, and we can work through sequencing, right? Because we want to do it monthly, so we can basically structure, and we'll collect the feedback. We'll see. We don't want to make it too long, so I guess we had a pretty good size meeting today, right? Pretty kind of same number of people most of the time. So if you'd like to give a full-length talk as well, let me know. All right. Any other questions or suggestions? Well, if not, I want to thank everyone. It was really good to meet.
I had one more thing to mention, maybe before we get out of here. So this is I don't know who started these things, but it's quite interesting. Have people seen these quarantine talks, or the Q-Orantine talks? It's a sort of self-organizing quantum talks series. So there's just basically some Google Doc somewhere on the web where people are typing in if they want to give or see talks. It might be something people here are interested in. I just dug up the link for it. I can't for some reason I can't type to everyone, so I'll just type it to Alexi, and maybe you might be interested to put that on the website or to pass it to the other people that are here.
I think this is the hosting setup of the chat, that you can only chat with the host for now, but we'll should make it easier. Yeah, I got the talk. I'll share it. Thank you for bringing this up. I'll see what it is, and my goal is to basically, connect as many people as possible working in the field. So I'll definitely will reach out to these folks and see if we can, join forces in bringing more talks to people. So that's great. Thank you.
Aleks, I just had a quick question before we go. I wanted to ask you, I really enjoyed your talk. It was really awesome. And I have some questions about, historically, it seems like the gates are rather arbitrary in quantum computing. And I was just kind of wondering, when you have something more definitive, like essentially this ZX calculus, is there sort of a way, like would it be helpful if Qiskit or other programs, if the quantum computer could be programmed directly essentially in more fundamental quantities than, let's say, the gates that are used traditionally? Or, I mean, is there a way of understanding that process at the end of essentially extracting the gates that are normally used in quantum computing from essentially the more fundamental spiders? Is there something to be said for, I don't know, is there some way of maybe, is there a way of systematizing that historical legacy, or is it just not really an issue? I don't know.
Yeah, I don't know. Yeah, I guess when it comes to you know, thinking about theoretically building circuits, there were basically any combination of gates you'll come up with. It's just very hard to find a set of gates which is not universal. I mean, it's
right. I guess that's true, right? You can make
so
it.
So yeah, there is a kind of arbitrary nature to them. Something that does seem more natural to work with are gates that look much more like kind of Pauli type interactions or something. So the multi-qubit gates or something, you know, to think of something like exponent of some phase parameter times ZZ or something is much more natural than a control NOT gate or a CZ or something. That sort of shows up in this ZX notation, and I guess that is also kind of bared out in the hardware. I think, not being a hardware person myself. But yeah, I mean, I think it is useful to think in a way that's not kind of married to a particular set of gates. So.
Yeah, I guess I'm just wondering, is there a way of translating like spiders more directly into sort of what's available on the quantum computer in terms of is it, I guess, are there some lessons in even the compilation for essentially those sort of building the fundamental gates on the quantum computer as well?
Yeah, maybe so. I mean, our extraction is still very very tied to controlled NOT gates in the way that it works, but I don't think there's any particular reason it needs to be that way. So
Okay. So that one could, in principle, as you said, go to a more natural structure. If this was more natural, one could migrate to a more natural way of coming up with a different set of universal gates, essentially. Okay, cool. It's really interesting. It's fascinating stuff. Is there one more question? Is there a good paper that you would recommend to review some of these things just to get a better understanding of the basic ideas? Beyond your life.
Yeah. So the kind of the best paper for what specifically I talked about is there's a paper on the archive.
Okay.
I think if you look for my name on the archive, it's called Graph Theoretic Simplification.
Okay.
Of something using ZX calculus. It's also appearing in Quantum quite soon. So if you watch quantumjournal.org, it should show up there, I think, within a couple of weeks.
Okay, awesome.
There's also a big pink book with a dodo on the front, which I meant to plug, called Picturing Quantum Processes, written by me and Bob Kuka, which explains kind of a whole lot of things around this approach.
Okay, cool. So there's
also, I mean, something that might be interesting there is we spend quite a lot of time looking at density operators and mixed states and stuff in this kind of more diagrammatic language. So.
Okay, nice. That would definitely be interesting to take a look at. Okay, cool. Is that like Amazon or just, it's on, is it available at Amazon or something like that to just get a copy?
Yeah.
Yep. Awesome.
All right. Thanks, guys. Any other questions or suggestions? As always, the information on the website, we'll post the recording of a lot of people asked for the recording of the talk, so we'll post them under the same entry once we're done, which should be very easy, and so hopefully more people will learn. I will share the links there. If there is a feedback form, quick questions, just let me know. But thank you very much. It was really great. So Aleks, David, LeeAnn, you're the pioneering speakers in our inaugural series, and John, pioneering lightning speaker. I hope more folks come forward. Hope to see you next month. We'll publish the next date on the same site, quantum.sv, and we'll email you guys. Thank you very much, and hope to see you soon. Stay safe.
Thanks.
All right, Alexei, thanks a lot. You too.
Thanks. Bye-bye. Bye, everybody. See you soon.